Okay. All right, now we're moving on to problem 6. Now I'm using the whole board for this because problems 7 and 8 we need a lot of space for. So let's move forward. So now, all right, so this we talked about in class, and this is where I got a little bit stumped, but I have it totally clear. So we are totally straight as far as this is going to go. So we're looking for the pH of a 0.1 solution of HNO2 that starts out at 2.17, and we want to know what happens to the pH if we add some base to it, which is NO2 minus, and we have that at a particular concentration. This question is in preparation for the next two questions. Okay, so if the pH is equal to 2.17, we know something about the concentration of H+. Then we remember that H+ can be calculated as the -10 to the negative pH. We have a pH, so we know that the concentration of protons in this solution up to this point, without adding anything to it, is 10 to the minus 2.17, which is equal to 0.00676 molar. Okay, so that's what we have, which is very, very small. So we're going to make some assumptions. We're going to make some assumptions, but also we're going to look at this equation. So first, okay, so this is our initial concentration of H+, right? And this, like we said, is very small and nearly negligible or insignificant. Okay? Here's the reaction. We have HNO2, and it's dissociating to form H plus and NO2 minus. Okay? So this is the reaction that is occurring. Now, we know that we are starting initially with a concentration of 0.1 of HNO2. So we go ahead and put that in. We also are assuming that we don't have any initial protons because we are assuming that this value here is very, very small. So in reality, not in reality, but we normally, when we would solve these, we would subtract. First, we would find out how much X it would be for this pH. This would be equal to X, as we did in some previous problems, right? We could say that we're starting with this, but let's assume that it's nearly 0, okay? That's a long answer for let's assume that this is nearly 0. And since this is nearly 0, and we are given that we're starting, that's increased by this 0.1 molar, it would be X plus 0.1 molar. But like we said, X is really small, so we're assuming that we are initially just starting with 0.1 molar NO2. Okay, there's a long answer for saying we're starting with 0.1. So this is what we're initially starting with. We're given that the concentration is 0.1, the dissociation for the pH to be equal to 2.17, it gives an X value of 0.00676, very small, assuming that to be 0. So then for NO2, that would be equal to 0.1 plus X, but like we said, X is very, very small, so we're assuming it to be just 0.1. All right? Now the change. Now we're going to look at the percent dissociation. I know we said we weren't considering it before, but we are now. So that's, wait a minute. Minus X, yep. plus x and plus x. Just roll with me on this, okay? Equilibrium concentration gives us to be 0.1 minus x, x, and 0.1 plus x, okay? So before, when we didn't add anything to it, and we just had just the weak acid itself, when we had our equilibrium concentrations for H plus was x, and for NO2 it was just x. But we've added some additional 0.1, okay? So now let's then figure out our x. And we're going to use this same old relationship. Ka is equal to H plus over NO2 all over H NO2, right? Yes. And so that leaves us with Ka being 4.5 times 10 to the minus 4 equaling x times 0.1 plus x all over 0.1 minus x. But we can make some approximations, right? Again, so we're now assuming once again that this x is going to be way smaller than (0.1). So that's going to make these go away. Now we remember from a past problem that we calculated to verify that this approximation was valid. We found that the percent dissociation was 0.45%. Super small. We're going to say that it's still valid. This is going to be true once again. So since that is true, let's go on and keep solving. So 4.5 times 10 to the minus 4 equals x times 0.1 over 0.1. These are going to go away, so we assume that x is equal to 4.5 times 10 to the minus 4, which is really the pKa, right? And so then we then take, we say that x is equal to the number of protons, the proton concentration, which is H plus. X is equal to 4.5 times 10 to the minus 4, right? So in order to get the pH, that's going to be equal to the negative log of the proton concentration. Instead of writing H plus, let me just go ahead and write 4.5 times 10 to the minus 4. And that calculation ends up being 3.35 which is equal to the pH. And there's our answer. And so we then see from this, we're saying that if we add a little bit of base, we get a pH of 3.35. Now, does this make sense? Yes, it does, once again, because we started with a pH of 2.17. When we added a little bit of base, like we did over here, we ended up with a slightly higher pH. And that's what we get when we add base, is a higher pH. So again, this makes sense, so that's great.